Software deployment cycles are accelerating, and traditional automated UI testing is reaching its limit. The moment a button shifts or a locator changes, brittle test scripts shatter, leaving QA teams with a massive maintenance backlog. To understand why this happens, we can look at an empirical study of testing efficiency performed on a car rental web application. This chart tracks different test generation methods. Even using GPT-4, the system identified only 67% of bugs after 46 steps. However, action state modeling used the same 46 steps to reach a flawless 100% detection rate. These results suggest that for complex systems, the bottleneck isn't the processing power of the AI, but the underlying structural logic of the model itself. This logic is the basis of model-based testing, or MBT. Instead of writing individual scripts, engineers represent expected system behavior as a mathematical model from which a tool can automatically generate test cases. This approach dates back to the 1970s with IBM's TELDAP project, designed to move testing away from manual scripts toward a systematic engineering discipline. But MBT faces a common problem: poor abstraction. When teams try to include every detail in a single map, the graph expands exponentially, creating a model explosion that is too complex to maintain. To keep models manageable, the ISTQB framework suggests focusing on specific targets: the system model for internal logic, the environment model for user behavior, or test models for business workflows. To reach that 100% detection rate without the risk of model explosion, we have to look at how a two-phase architecture and action state modeling work in tandem. Many teams fail with MBT because they rely on shortcuts that compromise the validation process. The most significant of these is the single source problem. In an effort to save time, testers often take a developer's system design document, like a UML diagram, and use it as the basis for their test model. If an error exists in the design document, that mistake flows into the source code and the test model. Because they share flawed logic, the test passes. This is a false oracle. You've verified the blueprint, but not what the user needs. Another trap is the use of GUI ripping tools to automatically generate models by scraping web pages and clickstream data. These tools are context blind. They capture every possible link and button, generating high-noise models that force engineers to spend more time cleaning up useless paths than they would have spent modeling by hand. Manual modeling by a domain expert acts as an early form of static analysis. It allows teams to identify contradictions and missing logic in the requirements before a single line of code is ever written. Even with a good model, maintenance remains a barrier if the architecture is one-phase. In a one-phase model, high-level business rules are mixed with low-level UI locators, such as XPath tags. If a single button identifier changes on the front end, the entire logical graph shatters. The solution is a two-phase architecture, separating what the system does from how it is executed. Phase 1 is the abstract business model. This layer focuses solely on the logical rules of the application, containing no UI code. Phase 2 is the test adapter, translating those logical paths into specific commands for an automation framework. This keeps the system dry. Don't repeat yourself. If the UI changes, you only update the Phase 2 adapter. The complex business logic in Phase 1 remains untouched, and your entire test suite is instantly restored. Once the architecture is separated, we must decide how to design the logic within Phase 1. This method found 93% of the bugs, but it requires engineers to write complex guard conditions directly into the model nodes. This leaves testers with a choice: a simple stateless model that misses deep bugs, or a complex stateful model that is difficult to build and prone to state explosion. Action state modeling provides a middle ground that achieved the 100% detection rate in the study. It uses a simple rule. A step consists of a user action and a system response. A state node is only added when the logic specifically requires a change in context. Because the flow of the scenario itself manages the logic, engineers don't need to write complex code inside the model. When combined with a zero-switch algorithm, this model generated exactly 8 test cases covering every logic path and identifying every bug. This shows that mathematical optimization can produce much more reliable results with fewer steps than generative AI guessing. To ensure these generated test suites are reliable, architects use 3 quality gates. First is syntactic quality. checking that the model follows the correct grammar of the modeling language so the generator can process it without errors. Second is semantic quality, ensuring the model correctly reflects the business requirements to avoid the false oracle problem. This is achieved by simulating the model. Stakeholders can watch an animation of the logic to verify it behaves as intended before code is executed. Finally, pragmatic quality ensures the model is readable and maintainable over time. This is handled by linking model nodes directly to the original requirements, making it clear which parts of the model need to change when a feature is updated. Together, these elements form a pipeline designed to handle the rapid iterations of modern DevOps. Because the Phase 1 model is decoupled from the UI, domain experts can begin modeling during the design sprint while developers are still planning their work. This allows a team to have optimized, executable test cases ready before the first line of application code is even written. This makes action state modeling more than a speed optimization. It turns the QA process into a predictable, mathematically optimized part of the development lifecycle.